Have you ever wondered what the internet's invisible footprint looks like? How much energy sits behind a single search, a photo saved to the cloud, or an AI answer? Today I want to start with that question and then tell a short story that will make the numbers feel less abstract. As it was narrated to me, a couple of years ago, a local community center somewhere switched from paper sign-ups to an online booking form. And then somebody remarked that moving to cloud would save trees. It did in small ways, but the same move also meant that a server somewhere now had to be kept spinning for those bookings, and someone had to pay the electricity bill. The shift was neither purely green nor purely grey. It was a trade-off, and exactly the kind of trade-off we need to understand if we are serious about a sustainable digital future. Today's episode is a long, careful conversation about those trade-offs. We will travel from data centers humming in Northern Europe to code running on laptops, from the policy halls in Brussels to the startups working on product passports and blockchain traceability. I'll bring you facts, stories, and a practical view of what's changing now and what to watch for next. I'll draw on two recent in-depth research reports I have been reading, which collected the latest developments, stats, and case studies about green digital innovation in 2025. These sources give us a grounded picture of where the digital sector stands and the decisions that will shape whether it becomes part of climate solution or part of the problem. When we talk about sustainability, most people picture renewable energy, public transport, or better insulation in buildings. Fewer people picture software or data centers. Yet, the digital sector already uses a non-trivial slice of global energy. Recent work collected in the reports I am using shows that digital technologies consume a rising share of energy and greenhouse gas emissions, and that data centers in particular have been growing their electricity demand rapidly as AI and cloud services expand. Without improvements, data center power demand could rise substantially through this decade. Those are not abstract projections. They are numbers with consequences for grids, water use, and policy design. At the same time, the same digital tools, artificial intelligence, sensors, real-time optimization, digital twins, and transparent supply chains are among the most powerful levers we have for reducing emissions across other sectors. This tension, digital tech as both problem and solution, is the core of this episode. Europe has placed itself at the center of that tension, committing to regulatory measures and public investments that force the question: can we scale digital services without scaling their carbon footprint? The reports show Europe pushing hard on rules for data centers, investing in climate-grade supercomputing and digital twins, and promoting standards for software carbon accounting. To understand the landscape, it helps to think in four connected layers: hardware and infrastructure, software and algorithms, data and lifecycle management, and policy plus market mechanisms. Infrastructure means data centers, networking, cooling systems, the physical chips and servers, and the energy sources that power them. The research highlights how hyperscale cloud providers are investing in renewables and new cooling techniques, and how European supercomputing projects are prioritizing liquid cooling and renewable electricity. These infrastructure shifts can cut the carbon intensity of computation, but they require large capital investment and strong coordination with local grids. Software and algorithms represent where developers can make an outsized impact. Green software engineering is not just a slogan, it's a practical set of design choices that reduce compute waste, from algorithmic efficiency and model pruning to scheduling heavy jobs for times when grids are greener. Industry groups and foundations are building the measurement tools and standards that let software engineers make this visible and measurable. Data and lifecycle management are about embodied carbon, e-waste, and circularity, extending device lifetimes, reusing server components, and designing products for repair all matter. In Europe, this connects to digital product passports and circular economy rules that push manufacturers and cloud operators to be accountable for the whole life cycle of hardware. Finally, policy and market mechanisms, rules, public procurement, buyer expectations, and investor demands set the incentives. Europe's strategy blends regulation, data center reporting rules, and push toward climate-neutral centers with public investment in green HPC and digital twin initiatives designed specifically to help planners and policymakers. When policy aligns with private investment and engineering practice, scaling low-carbon digital services becomes plausible. The conversation happening now in Brussels matters for the rest of the world because Europe is trying to codify what green at scale looks like. It's tempting to treat Amazon, Microsoft, and Google as interchangeable when we talk about the cloud. But each has chosen different levers, and those differences are instructive. Google has invested heavily in what it calls carbon-aware operations, combining renewable energy purchases with smart scheduling and a central fleet approach that keeps servers more fully utilized. That approach reduces the need to buy new hardware and shrinks embodied emissions. Google's internal reports referenced in the research show very large improvements in energy per AI query through model and infrastructure engineering. That is a demonstration that architecture plus software optimization can yield rapid improvements in energy per operation. Microsoft has pushed ideas like carbon-aware computing into public view, working with partners to define metrics and publish open source SDKs that allow workloads to be shifted to lower carbon periods or locations. Microsoft also takes a portfolio approach, pairing renewables, storage, and low carbon grid solutions to give customers choices for cleaner compute. This dual approach, technical tooling for developers plus energy procurement for infrastructure, is an example of how platform providers can nudge entire ecosystem. AWS has moved aggressively on renewable PPAs and on tools that make carbon visibility native for enterprises. It also experiments with efficiency measures across its global colo footprint, while offering customers insights into their cloud carbon footprints. All these cloud providers' actions matter because most companies now lease compute rather than build their own data centers. The provider choices determine the carbon intensity of enormous swathes of global digital activity. Europe is not waiting for industry alone to solve the problem. Two parts of Europe's response are worth underscoring. The first is investment in highly efficient supercomputers under the Euro HPC effort. The continent's HPC nodes prioritize renewable sourcing and advanced cooling systems, demonstrating that high-end compute can be married to low-carbon design. These machines are not only for academic curiosity, they run climate simulations and feed initiatives that aim to improve climate resilience across the continent. When computation that helps cities plan for floods or utilities optimize grids is itself greener, the multiplier effect is significant. The second is the Destination Earth initiative, a digital twin program intended to provide high-fidelity climate simulations for adaptation and policy making. Destination Earth requires vast compute resources, but it has been designed to run on Europe's greener, more efficient HPC networks. The point here is structural. If you ask digital systems to inform climate policy, those systems must be built with climate impact in mind or risk hypocrisy. Europe's insistence on mandating reporting for large data centers and aiming for climate-neutral data centers by 2030 is an attempt to close that contradiction. To say that software should be green is easy. Implementing it is less obvious and significantly within the control of development teams everywhere. Green software engineering includes designing algorithms that require fewer cycles, batching non-urgent tasks to run at lower carbon hours, reducing data transfers, and choosing efficient data formats. It also includes the discipline of measuring energy and emissions linked to software execution, so that engineers can trade compute for user-facing improvements with visibility into the environmental consequences. Tools and standards are maturing. Foundations and industry coalitions are publishing the metrics and the training programs needed to bring carbon awareness to the dev team level. Adoption still lags, in part because teams are busy and incentives are misaligned. But the early adopters are showing that the engineering cost is not as high as feared, and that some changes can simultaneously reduce bills and emissions. Artificial intelligence gets top billing in headlines because it is both a major energy consumer and a major efficiency opportunity. On the one hand, training and serving large models can be energy intensive, increasing electricity demand and water use for cooling. On the other hand, artificial intelligence is being used to shrink energy use in data centers through predictive cooling, workload placement, and resource allocation. And it can also help other sectors, transport, manufacturing, agriculture, reduce their emissions. The studies underpinning this episode document intense work to make AI itself more efficient, from model quantization and sparsity to smarter serving architectures. But there is a rebound risk. As AI becomes cheaper and more useful, demand for compute can grow faster than improvements in energy cost per operation. This is a policy and design problem. To get the best outcome, we will need to couple efficiency gains with incentives to manage demand, better measurement, and strong procurement choices that privilege lower carbon options. We often focus on the electricity that runs compute, but embodied emissions in hardware, the carbon used in manufacturing, transporting, and eventually disposing of servers, routers, and devices are large and often overlooked. Extending the life of devices, reusing server parts, and shifting to product as a service models can reduce embodied emissions. The research shows real gains available through reuse programs, and it highlights how regulators in Europe are encouraging digital product passports to improve traceability and repairability. These moves are practical and sometimes unglamorous. They involve logistics, reverse supply chains, and tight coordination between manufacturers, cloud providers, and recyclers. But they're essential. A focus solely on operational energy without addressing embodied carbon creates perverse outcomes where we replace hardware too often and pay the carbon cost upfront. Across Europe and globally, there are projects that show different aspects of the transition. Companies are pairing data centers with local district heating systems to channel waste heat into communities. Others are experimenting with liquid immersion cooling to dramatically reduce energy requirements for thermal management. Cloud providers are signing long-term renewable contracts and building storage and microgrid capacity to smooth intermittency. City planners are using digital twins to run what-if scenarios that inform infrastructure investments. Utilities are using AI to forecast demand and integrate more renewables. And startups are building products that enable circularity, such as platforms to verify recycled content or marketplaces for refurbished enterprise kit. The collection of reports I used highlights many such pilots and early deployments in 2024-2025, suggesting that the shift is no longer only theoretical. Even with pilots and commitments, the transition stalls in predictable places. The reports point to several recurring barriers. The first is measurement. Without agreed metrics and easy tooling, organizations cannot see the emissions of their software and are therefore unlikely to prioritize changes. The second is financing. Some sustainability changes require upfront capital, and the payback is either long or hard to prove. The third is skills. Developers, operation teams, and policymakers need new fluency in energy and carbon concepts to make the right trade-offs. Finally, there is the grid and supply constraint. Even the best data center is still subject to the availability of clean power in its region. These bottlenecks are solvable, but it will take deliberate policy and coordinated investment to overcome them at scale. Investments in the green digital transition cluster into infrastructure, tooling, and human capital. Infrastructure investments include greener data centers, microgrids paired with storage, low carbon PPAs, and the next generation cooling. Tooling investments include software for carbon-aware scheduling, measurement frameworks, and life cycle traceability platforms. Human capital investments mean training engineers in green software practices and funding interdisciplinary teams that bridge energy and software. The research notes that the early stage financing dipped in early 2025 in some segments, but larger strategic capital and public funds remain available for projects that demonstrate both climate impact and commercial viability. The message is that investors are drawn to solutions that lower cost and risk while also delivering clear climate benefits. If you run a team, lead a product, or build a software, 3 practical directions will move you from intention to action. First, measure. Start with basic visibility into compute, storage, and networking costs, and pair them with carbon intensity data where possible. Second, prioritize low cost, high impact changes such as turning off idle services, batching non-critical tasks, and reducing redundant datasets. Third, partner with suppliers to understand their energy mix and ask for lower carbon options in procurement. These steps are not glamorous, but they are achievable and they build momentum for larger shifts like scheduling changes and hardware upgrades. The research underscores that modest operational changes can quickly drop bills while also lowering emissions, a crucial political and commercial argument for adoption. A period from 2025 to 2028 will be decisive in at least 3 ways. 1. Regulatory tightening in Europe will force transparency and create minimum efficiency baselines for large data centers. These rules will change the economics of where and how companies choose to run heavy workloads. 2. Carbon-aware tooling and metrics will move from academic projects to embedded features in cloud platforms and orchestration tools, making it easier for dev teams to code for lower carbon outcomes. 3. Hardware innovation. Most efficient AI accelerators, wider adoption of liquid cooling, and improvements in energy storage will shape the cost of clean compute. The combination of policy, tools, and hardware is what will make the difference between incremental change and systemic decarbonization. We must also be honest about distributional effects. Many of the most advanced infrastructure projects and low carbon procurements are happening where capital and grid flexibility exist. If Europe and wealthy regions tighten rules and capture the low carbon markets, energy intensive digital workloads might shift to places with cheaper power but dirtier grids unless there are coordinated standards and trade policies. The research suggests that aligning policy across regions and building international frameworks for digital decarbonization will be necessary to avoid outsourcing emissions. This is a both political and technical puzzle, and it matters for the legitimacy of any global green transition. When the community center, the story of which I mentioned at the beginning of this episode, moved its sign-ups online, no one intended to raise emissions. They intended convenience and lower cost. That small example captures the essential truth. Digital transitions change where emissions happen, sometimes lowering total impact and occasionally increasing it. The question for engineers, executives, and policymakers is not whether technology is neutral. It is whether we design and deploy it with an understanding of its environmental consequences. The reports I relied on for this episode show both urgency and opportunity. They document significant energy use and warn about unchecked growth in compute demand. They also document practical advances in cloud procurement, cooling, software design, supply chains, and public investment that together make a decarbonized digital future plausible. The work is underway, the options are visible, and the next steps are organizational and political, not purely technical. If this episode leaves you with one practical impulse, let it be this. Find one thing you can measure within your digital footprint next week. It could be a service that sits idle, a data set nobody uses, or a clear request to your cloud supplier for emissions metrics. Measurements is where choices become visible and where the slow work of change begins. This conversation is part of a larger experiment. We are learning how to make digital systems serve climate ambitions rather than undermine them. The path will require engineers who care about carbon, investors who value long-term resilience, and policymakers who design smart regulations rather than blunt instruments. Europe's mix of policy, public investment, and standards work gives us an early laboratory. The rest of the world will learn from what succeeds and what stumbles. Thank you for listening to this deep dive into green tech innovations and what they mean for a sustainable digital future. If you found this episode useful, share it with someone building software or running infrastructure. The decisions those people make will shape whether the next wave of digital growth helps or harms our climate aspirations.